Okay, so let's again consider the infinite plane with uniform surface current density lambda. So let's look at the plane edge on, so that the plane looks to us like that, and draw the current coming towards us, right? So we can think of the current as really an infinitely long collection of infinitely long current carrying wires, all with current towards us. So we know that the geometry of this magnetic field must be such that the field above is parallel to the surface where the current lives, and the same thing is true below because of symmetry. And so, and by the right-hand rule applied to that part of the Biot-Savart law, right, the current, we can think of these wires having little pieces of current dl coming straight at us, and if we want the field below, then the middle finger points downward and our thumb points to the right, so we know that the field has that geometry below, and therefore it has that geometry above, because the principle is that magnetic fields curl around the source, and here they are curling around the source. So we know that the magnitude of the magnetic field is mu naught lambda over 2. We derived that from Ampere's law. And now let's consider a rectangle, or let's make it a square, so it's a square of side L, and let's consider the maximum magnetic flux that we can produce through this square. So phi b max, right, what is that? Well, it's the maximum value of this quantity, the integral of the magnetic field on the surface, and so orientation matters. So we want to place this square such that magnetic field lines go straight through there, and so if we place it, let's draw it here blue. If we place it like this, right, here's our square, side L. If we place it like that, the field lines everywhere on the surface of the square don't penetrate the square. Right, they don't go through the square, they just lie on the square, and the dAs, right, the dAs of the surface here are pointing normal to that surface, so B dot dA is 0 at every single point, and we get 0 flux in that case. Right. The way we want this to look is that, right? So that's the side of the square, side L, and it looks to us like that. We don't see the surface because it's oriented like this, and so the field lines go straight through it. And when we do that, because the magnetic field is everywhere the same, it's a constant, so it's mu naught times lambda divided by 2, and we integrate over the surface to get the area of the square, which is just L squared. So that's the maximum possible magnetic flux through a square of side L. Now let's imagine that we have a cube. So let's say that we have a cube. It could be the cube of side L. So all the sides are of length L, something like that, and we can place it here such that maybe let's continue this, and we'll put the cube over here, so we'll make it blue. So let's say that we place it like this, so that half of it is above and half of it is below, so there's clearly current going through the cube, so that's a cube, right? If we look at it from this perspective, we don't see the other sides, but here is current clearly going through the cube. So there's current enclosed in this cube, but that doesn't change the fact that the magnetic flux through this will be zero by Gauss's law, so that the magnetic flux through the cube, we don't have to worry about doing any complicated calculation because we know that the magnetic flux through a closed surface is zero because magnetic fields circle around. But if we insisted on doing the calculation, we would notice that the magnetic field is pointing, so on this side the magnetic field is pointing that way. All right, so we have a few field lines here. Over here it's the same thing, it's pointing that way. Here we have the field lines pointing in the other direction. They're all the same length. And on the top surface, field lines are pointing here, they're pointing that way, and here they're pointing that way. But they don't contribute to the flux on the top, on the bottom. And on the front side and the back side, they also don't contribute anything because the field lines are all that way, so they don't penetrate those sides. We get flux through here, which is directly out of the out of that left-hand side. So we get phi b if we wanted to do the calculation directly, right? From that side, we get that would be the magnitude of the field there is mu naught lambda over 2 times the top side, right? The top side is L, but we get field lines going through that way only halfway. So this side is L over 2. So we get L squared over 2 here, and we get a factor of 4. But then we have an equal and opposite contribution from this side, which is therefore minus mu naught lambda L squared. Let's write it all just like that. That cancels to 0. Then we have, from this side, we have the same thing for the bottom side, right? We get mu naught lambda over 2 times L squared over 2, and negative for the top side because we haven't drawn the dAs, so let's draw them here. Right, where we get positive, the dAs are pointing in the same direction as the field. Where we get negative, they're pointing in the opposite direction. The dAs are always pointing normal to the surface. So positive flux, negative flux, and negative flux, and they all balance out. And that, of course, will give us 0. So notice that if we place the cube such that it looks like this, so it's tilted, that looks more like a rectangle, that side, but let's assume that's our cube, that's a square, and the calculation would be harder, but nonetheless it would have to add up to 0 because we have a closed surface and magnetic field lines will come in somewhere and come out somewhere else, and the flux will ultimately cancel.